last class we were discussing the switched mode regulator. We started discussing and we understood about the converter, DC to DC converter. This converter by nature you can see what it is. We saw that V naught is going to be equal to V I tau by T, and we said by varying tau by T, which is called duty cycle, okay, we can maintain V naught constant when V I is changing. This kind of thing is done by using this information of control. That is, I am sampling V naught and comparing it with V reference, just as I do in the normal voltage regulator. I sample V naught. How do I sample V naught? I will take V naught and take R1 by R1 plus R2 of V naught, compare it with V reference, and that was fed to earlier a comparator, which was actually acting as an amplifier to control the base current of the pass transistor, so that the pass transistor voltage drop is getting adjusted depending upon the error here. So, that is the pass transistor was working at that time in the active region. Now, I am again once again sampling V naught R1 by R1 plus R2, comparing it with again a V reference, giving it to a comparator, but this comparator makes sure that the transistor is never going to continuously operate in active region, but will be always in the mode of what? Switch. The transistor should be acting as a switch. So, we have to make sure that it acts as a switch. That is done by giving what is called regenerative positive feedback, right, to the comparator, and the comparator is nothing but a Schmidt trigger, right. So, it makes sure that it always operates either in high or low, so as to drive the transistor switch either to off state or to completely on state or saturation state. So, this is what is done by using this piece of information. Now, how do I do it? How do I actually change the tau by T? That means, now I make sure that the duty cycle for which the transistor is going to conduct is going to be controlled by this information, which is the output sample voltage and reference. This difference is now going to control the duty cycle. So, it is a voltage controlled duty cycle generator that is required for this, a DC voltage controlled duty cycle generator. In communication terminology, this circuit is called pulse width modulator. Now, this pulse width modulation scheme is very important in making the stage work in what is called class D mode. Okay. The transistor is always going to work either in saturation or in cutoff. So, this kind of operation is called class D operation, okay. And this principle is used in designing power amplifiers, in designing obviously controller circuits here, and also in let us say communication, okay, for modulating the width by means of signal. So, a variety of applications are there for this information. It is also used in multipliers. Okay. Tau by T, if it can be voltage controlled, then it becomes nothing but a multiplier. We will see all these things when we discuss later, okay, about IC multipliers. But for the time being, it is enough if you know that this principle is one of the most important principles in controls, communications, okay, in all these areas. So, V I into tau by T is going to be maintained constant by the switched mode regulator. Okay. We will see the converter basics further. Yesterday we discussed all about the waveforms, okay, after making certain approximations. This is the input waveform, okay, after it is switched is going to V I and 0, that is made sure by this. Okay. These are complementary switches. Now, there is no need for a sort of control switch like this here. This operation can be done simply by a diode, which is again a switch, but it is a 2-terminal switch. Okay. It is switching on by making it get forward biased. How do I make it get forward biased? By pumping in a current in the forward direction, it gets forward biased. This is important. It is biased by means of a current. Okay. By pumping in a current in this direction, it gets forward biased, and at that time voltage across it is 0. Okay. Then by applying a voltage in the reverse biased direction, it is open circuited. Okay. So, this is the way a diode can operate as a switch. By applying a voltage in the reverse direction, it is switched off. By applying a current in the forward direction, it is switched on. Okay. So, this is made sure because when V I is applied, the V I voltage is appearing directly across the diode and diode is off. Do you see that? So, when V I is, this is connected and this is connected, V I is across the diode and it is reverse biasing the diode, and the diode makes sure that this is off. This portion of the thing is off. Next, when this is open, the current in the inductor cannot change suddenly. So, it continues to flow. Current in the inductor cannot change suddenly. It continues to flow, okay. But since the current has to be sustained, the current is going to bias the diode in the forward direction. Okay. So, the diode is getting on automatically, okay, and the voltage across it is sustained to be 0. So, automatically this is 0 and this is V naught, and therefore, the current starts decreasing in this direction. That is what we saw. Okay. So, over this period, as long as V I is not connected, the current is going on decreasing linearly, and suddenly again this switch is on. Okay. The diode is off immediately and the current is going to increase. Okay. So, this is what we saw in the last class, except that we have changed this switch now. Otherwise, the same thing can be done by using complementary switches here, which gets, let us say, Q here as its input and Q bar here. Okay. So, Q and Q bar as the gate inputs of the, let us say, FET switches here. That also is possible, but with using only one control switch and a diode, the same thing can be done. So, the entire converter has the following components now: a switch, which is obviously a transistor switch, and diode, which is a power diode now, because it has to carry the load current anyway, right. So, inductor, again the inductor also has to be designed to carry the load current, okay, and a capacitor rated for that voltage, whatever voltage. Okay. So, these are the things that are necessary. One important point in the design of this is that the inductor has to be wound with thick wire because you want to make the resistance, okay, as small as possible. Simultaneously, of course, we have to also permit the current to load current to flow through the inductor. So, this is one part of the design, and the capacitor has to be a good capacitor. I mean, you might say, okay, the leakage resistance is going to be part of the loads. No, there should be low series resistance, okay, associated with the capacitor. Why? We have assumed under our discussion of ripple that the entire voltage, this voltage flows through the capacitor, okay, and the capacitor has been taken as ideal capacitor, where the voltage across the capacitor is 1 over C integral I dt. That is only when it is ideal. If there is a series resistance, okay, the ripple will be totally because of this current flowing through the series resistance. So, if you find the ripple of the output is higher than what you have estimated by this approximation, okay, which is 1 over 8 times delta I L into T into what else? Peak to peak ripple. 1 over 8, okay, delta I L into T times by C. That is all? Right. So, this is the ripple, okay, peak to peak ripple, if the resistance through this is assumed to be in series with this is assumed to be 0. Okay. Otherwise, this triangular waveform is going to cause a drop across it depending upon the value of the is I into R, that is delta I into R. Okay. So, please remember this. This is quite often the mistake that is committed. You will be surprised to see if you are using a bad capacitor that the ripple is more than what you have estimated using this. Okay. Now, okay, you are now capable of designing a good converter. Now, we would like to see how to generate the control circuit for this. So, I would therefore take from this same combination of resistance that we used for the series pass regulator, we are using R1 and R2, sample the output. So, we get beta times V naught here. Okay. So, this is going to be compared using a comparator, let us say, with what? The reference. I would like to know whether the duty cycle has to be increased. If the input voltage is increased, okay, duty cycle has to be decreased. Okay. If the input voltage is decreased, duty cycle has to be increased. So, that information is obtained by finding out what this voltage is. Right. I want the output to be maintained constant. Okay. So, beta times V naught is compared with V reference, okay, such that duty cycle of this switch, whatever it is maintained constant. Now, obviously, this switch is, let us say, a transistor switch. Okay. Now, what else has to be coming into picture? This voltage has to generate a pulse train whose duty cycle is controlled by this voltage. Right. So, that can be done by using what? We can now use here let us say a triangular waveform and another comparator. Let us see how this is going to help. we are having a triangular waveform, let us suppose. Okay. Now, if a triangular waveform with peak voltage equal to Vp, let us say, and time period equal to t is applied to a comparator whose other voltage, input voltage, is connected to ground, what will be the output? Let us see. This is plus and that is minus. What will be the output? It's going to be a square wave. If this is connected to ground, okay, and you apply a triangular wave, output is going to be a square wave. So, if this voltage with which it is compared is not 0, but something finite, let us say it is this. What is it going to be now? It is going to high state during this period, okay. It will go to low state during this period. So, we can draw that. Supply voltage, let us say. So, this is the duty cycle, let us suppose, tau. So, what will this be then? T minus tau, right. So, it is going to generate, if I vary this, it will now generate an output pulse whose width is controlled by this voltage. So, this is nothing but a simple pulse width modulator, linear in the sense, okay. The width is going to be linearly related to the control voltage here. Okay. So, let us see how it is. This is the control voltage, this is Vp. So, this is Vc. So, using similar triangles here, okay, Vp by, that is Vp is the height of this triangle by height of this triangle, which is Vp minus Vc, okay, is nothing but T by 2 divided by tau, T by 2 divided by tau. So, we can now get some information about how tau by t is going to vary, how tau by t from this is nothing but how much is it, equal to half, okay, into 1 minus Vc by t. Is this clear? So, you can see a very simple idea for modulation, okay, using a simple comparator, that the duty cycle of this circuit is directly proportional to the control voltage. If this control voltage is, let us say, audio, I mean I am just discussing about a situation of pulse width modulator, not relevant to this. Okay. So, if this is an audio, then you have an output pulse width train whose width is modulated by the audio. Okay. And if this is applied to switch properly, okay, power switch, okay, it can be connected to a load, okay, which is having a pulse train whose width is controlled by the audio. Now, if it is connected to the load through a filter, you will get the audio output. That means, efficiency of that power amplifier is going to be theoretically 100%. That power amplifier is called class D amplifier. In this particular regulator case, it is used for control purposes, that is all, same thing, right. This information is used for control, not for other purpose. So, the control voltage we see here is going to modulate this train of pulses occurring at a frequency equal to 1 over T in a suitable manner, so that this voltage is same as this voltage, right. Okay. So, the output voltage will so adjust itself. This is like in the case of any negative feedback operational amplifier circuit. Okay. As far as this whole mode of operation is concerned, okay, you can say that there is some DC coming here, and the effect of DC is to maintain this DC voltage equal to 0, right, like in any operational amplifier structure. So, that feedback from here to this should be purely negative feedback. Okay. So, please remember that from here to this there is going to be a negative feedback situation, such that this voltage here is going to be controlled, so that the switches are operating in either on or off mode, never in active region. Okay. This is made sure by this kind of operation. So, this is one of the most popular scheme for switched mode regulator. Of course, there are other schemes where it is self regenerative. That means, if you give regenerative feedback, it itself can oscillate. The whole scheme of this structure can oscillate. Whereas here the frequency input is coming from external source. That means, I have to have a source here which can generate a triangular wave of desired frequency. So, here the frequency is known to you, design frequency is known to you. If it is made regenerative feedback structure and this itself is made an oscillator, then we do not know, we have to adopt complicated analysis procedure for finding out the frequency of oscillation. So, this is an externally controlled, the oscillation frequency is externally controlled pulse width modulated voltage regulator, switched mode regulator. So, this is quite popular, and therefore, you see most of these circuits, L, C, diode, and even the switch might have to be provided externally, because these are going to be power components, right. So, the rest of the components, control circuitry and the pulse generator and all these things can be put internally. So, you will get these pulse width modulators circuits themselves as ICs. The whole scheme will be available to you as a single chip IC, suitable for switched mode power supply application, including the voltage reference with what is that, 0 temperature coefficient, etc., etc. So, ultimately, therefore, we have been able to obtain a switched mode power supply whose output voltage can be maintained constant irrespective of the variation in Vi. So, I wanted to bring up this idea of pulse width modulation, which is an important idea repeatedly used in IC applications in variety of purposes, control, communication. So, now we are coming to one of the most important building blocks of analog VLSIs, that is operational amplifier. Operational amplifier as the name itself implies, is used for what? Operational purposes. The operation that we are meaning here are the mathematical operations. Okay. That is why it got the name operational amplifier. The mathematical operation of addition, subtraction, what else? Linear operations are what are talked of. Addition, subtraction, integration and differentiation. These are the four basic operations, linear operations, which are very much in usage in analog signal processing. Okay. So, that is what is meant by operational, okay, and for that purpose we have to have an active device block, and the most important device block which was readily amenable for such integration, okay, was operational amplifier. It required the help of a large number of active components to be put together so as to get high gain, open loop gain. Okay. Its nature of this business, operational, comes about because of high open loop gain, or we will now call it as, because this is an old concept, high open loop transfer parameter. Okay. It need not be gain, it can be voltage gain, current gain, trans resistance or trans conductance, resulting in 4 types of operational amplifiers, okay, all of which can be used for the mathematical purpose, okay, of addition, subtraction, integration and differentiation. Okay. It is historical accident that whenever we mean operational amplifier, we took it for granted that it is operational voltage amplifier. Okay. These days, because of the ease of fabrication and utility, functional utility of the circuit over a wide range of frequencies, okay, other operational amplifiers are becoming more prominent than operational voltage amplifier, which was the first amplifier that was integrated and made available in large numbers, and this became a basic building block for most of the analog signal processing systems. So, it is important that obviously we understand how this particular operational amplifier got sort of evolved in the whole process of design. And what is it? It is, for the timing, we will therefore consider first operational voltage amplifiers. Strictly speaking, if it is an ideal control source, what is it going to be called? Is going to be VCVS, voltage controlled voltage source, which can only be expressed by one parameter. I have told you earlier in your undergraduate days, one parameter, that is VCVS. Okay. We have discussed this in the feedback. Okay. That is, in order to get a VCVS, okay, we have to obtain, give H feedback, but the resultant parameter, which is going to be very near the ideal parameter, is the G parameter. So, this is going to be G21, okay, and this is 0, this is 0, this is 0. So, an ideal voltage controlled voltage source cannot be represented in any other parameter other than G parameter. What does it mean? If you try to represent an ideal, okay, voltage controlled voltage source by any of the other 3 parameters, the other parameters will become, or some of the other parameters will become infinity. Okay. So, if you want to represent an ideal voltage controlled voltage source, it has to be represented by G parameters. In which, if it is to become operational voltage amplifier, G21 has to go towards what? Infinity. So, G21 tending towards infinity and all these three other parameters tending towards 0 is the characteristic feature of a operational voltage amplifier. Okay. That is the starting point. And here we do not want to get it by means of feedback. This should be an open loop configuration which is just realized, okay, such as to make these parameters go towards 0 and this parameter alone go towards infinity. Now, let us see the essential design features of such a thing. Now, such a design procedure that I am going to enunciate now can be adopted for design of any of the active building block, okay, whether it is used for operational purposes or simply as a controlled source. Okay. So, you can discuss now different blocks which are going to be used as active building blocks. There are going to be 4 types of operational amplifiers and 4 types of controlled sources, all of which are useful in analog signal processing. Okay. And how ICs meant for these can be evolved, can be started off from these basic, okay, definitions. Now, if you are going to make this go towards 0, which is nothing but feedback parameter, obviously, this is feed forward parameter, this is input immitance, this is output immitance. Okay. I have told you about immitance parameters. Immaterial what the parameter is. Okay. So, immitance, input self immitance, this is output self immitance. In this particular case, it is G parameter here. So, it will be conductance or admittance, okay, and this will be resistance or impedance. Okay. So, this is made to go towards 0. What is it? This is going to 0 and this should go to infinity, both of which can be easily achieved simply by simple operation of, I have told you earlier, the reverse transfer parameter for a single device, if it is low, much less than, okay, forward transfer device. One way to increase this and decrease this simultaneously is by cascading, right. This will increase and this will progressively decrease. In the case of operational voltage amplifier, this is nothing but reverse transfer parameter, that is voltage feedback, okay, parameter. So, if it is let us say 10 to the power minus 3, if you use 2 stages, it will be 10 to the power minus 6. If you use 3 stages, it will be 10 to the power minus 9, okay, so on and so forth. Here one stage has got a gain of let us say 100. So, if you use 2 stages, 10 to the power 4, 3 stages 10 to the power 6. So, boosting this and simultaneously reducing this is done by a simple act of cascading. So, it is necessary that in most of these operational amplifiers, cascading is an essential feature for simultaneously improving forward transfer parameter and simultaneously decreasing the reverse transfer parameter. Now, something about this. We have to increase the what? Impedance or admittance has to go towards 0. Here we have to decrease the output impedance or output resistance. Okay. So, we have to take suitable measures to do this. Now, this can be done, we have seen earlier, in designing differential amplifiers, which will be the input stage of, okay, any operational amplifier, let us say differential input, by operating at very low current if they are bipolar stages. You remember this? Because Re is nothing but Vt divided by Ieq. Okay. Ieq, when it is made low, automatically Re is going to be low. But you have to take care that beta of the transistor does not decrease too much. Okay. So, we should not go to very low currents where beta also decreases, so that this increase in Re is just compensated for decrease in beta, and you do not achieve much of a change in input impedance. So, input impedance increase can be done by using Darlington pair at the input stage, by using FETs, JFET, by using MOSFET. So, this is the order in which input impedance can be increased, but we have seen the disadvantage of the input impedance increase. Remember that simultaneously offset is going to increase. Okay. So, that depending upon what application it is going to be used, we will decide whether it is wise thing to do or not. As far as output impedance decrease is concerned, right, again we have seen that output stage is, let us say, going to be chosen such that it is a low output impedance stage. Automatically the choice is common collector, okay, output stage. So, the entire thing can be designed by simply noticing what the ideal device parameters should be and accordingly making use of our. So, output responsibility is given to output stage, input responsibility of input impedance, high input impedance is given to input stage, then the gain responsibility is given to an intermediate stage. So, essentially in design of any op amp, okay, if you want to do it in a very efficient manner, you must have necessarily 3 stages. Okay. Input stage to take care of input responsibilities like input impedance, common mode swing, etc. Output stage for taking care of output responsibilities like output impedance, output voltage swing, okay, and short circuit protection, etc. if it is needed, okay, and intermediate stage, okay, to give the required high transfer parameter, forward transfer parameter, okay, which now does not have the input impedance and output impedance responsibility. Of course, we can put more number of stages so as to boost this up and bring this down, but that will result in the order of the system increasing. Okay. We would like to have the order of the system, total system also possibly less than 3. So, that when we use it in negative feedback situations for operational purposes, it does not give us trouble in terms of high frequency oscillation. So, what is called as third generation operational amplifier, this is a slow process of evolution, right. People did not come to this conclusion of freezing this number of stages here to 3 in one shot. Okay. They tried different combinations. The first tendency is simply cascade as many stages of amplifiers as possible. Okay. That resulted in severe problems of high frequency oscillation and also this common mode problem resulting in latch up problems, okay, etc. So, the user had several complaints about, okay, the op amp being not suitable in certain applications, etc. Okay. This kind of thing had to be got rid of, and therefore, people then said we will give the responsibility of the input to the input stage, responsibility of the output to the output stage, and the gain to the intermediate stage, thereby freezing the number of stages of most of these op amps, present day op amps, into 3 stages. Okay. We will discuss further about this op amp in the next class. Okay. So, we have here the input stage, intermediate stage, and the output stage, which is common collector. This is nothing but the differential amplifier which we have already discussed. This is nothing but a single common emitter amplifier. This is the way biasing is obtained. Okay. So, we will discuss more about this structure in the next class.